All right, welcome to lecture 4.4, trigonometric functions of any angle. This is following section 4.3 where we were looking specifically at trigonometric functions of a right angle. So without further ado, we will move forward. Okay, so our objectives for this particular lesson, we're going to use definitions of trigonometric functions for any angle, which is not going to seem very different than what we've already done here. We'll just give them different letters or names for the sides, since we'll be dealing with coordinate points. We'll use signs of trigonometric functions. Now, that sign is not the sign S-I-N-E function, but the sign as in positive and negative. We'll find reference angles, and we'll use reference angles to evaluate trigonometric functions. Okay, so I just wanted to start out with just a little overview of what we're moving towards here. And your book had this really pretty picture of the same wood scenery or wooded scenery here for all 4 seasons. And it's talking about cycles here. So it says cycles govern many aspects of our life, from heartbeats to sleep patterns, tides. These are all predictable cycles, and because of their periodic nature, trigonometric functions are used to model phenomena that occur in cycles. So I found this other picture of a graph of the periods of the solar cycle. So I thought that was an interesting image to include here too, just to show that, you know, it's sort of crazy and quite amazing that things that occur in our natural world can be modeled by these, you know, mathematical functions and things like that. So when we get further along into this course, that image that I have there for the solar cycle variation will begin to make a lot more sense. And if you remember, I believe it was at the end of lecture 4.1, I showed you the animation where it was the point was moving around the unit circle, and it was formulating the sine and the cosine functions, and so that's what that should remind you of. So since we are moving towards being able to talk about the trigonometric functions of any angles, I just wanted to give you a picture here at the bottom right of the type of angles that we may be talking about here. So if theta is an angle in standard position, remember standard position has the first side going along the x-axis, and then you have the terminal side coming off of that with a central angle located at the origin, or the vertex of the central angle located at the origin. But so we have this angle theta in standard position, and we're going to let point P with the coordinates x, y, and you can see it's in each of these little illustrations here. We have a point P somewhere on that terminal side of the angle. So we want that point P to lie on the terminal side. And so let's move forward because we have some blanks to fill in here. Okay, so we're going to let angle theta be any angle in standard position. So we have a picture of that down here. P has the coordinates x, y. And if this is a blank right here on your note, so if r, or the length of the radius, which is the hypotenuse of this right triangle that we form by dropping a line down from point P, using the distance formula here, we have that r is equal to x squared plus y squared. And that should be very reminiscent of the Pythagorean theorem for you as well, because the distance formula is derived from the Pythagorean theorem. When I'm teaching the distance formula, the first thing I do is draw a right triangle in the plane, and we start with the Pythagorean theorem. So, so that should be reminiscent of that for you. So the length of this segment R here is given by the square root of x squared plus y squared. And that is the distance from 0, 0, the origin, to that point, x, y. When we have this situation set up like this, we're going to define the trigonometric functions as such. Now, this is no different than the SOHCAHTOA that we talked about in lesson 4.3. We've just given these side names actual values, and they're the values of that point, because I would have to move x distance to line up under that point, and I'd have to move y distance vertically to get up to that point. So it's legal for me to call the two legs of that right triangle those coordinates, because they're actually a distance that we're talking about. So just to help make this clear, I'm going to label this triangle as our opposite, adjacent, and hypotenuse. So we have the right angle here. Side R is our hypotenuse. Side X is our adjacent, and side Y is our opposite. Okay, so I'm not going to write opposite over hypotenuse or all, that language for each of these, but I'll do it for sine here so that you can see that it lines up. So our sine is opposite over hypotenuse. So in this case, we end up with y over r. Okay, so just running through these real quick, that means cosine is going to be adjacent, or x over r, hypotenuse. Tangent is going to be opposite over adjacent. And then we know with the cosecant, secant, and cotangent, they are just the inverse of their partnered functions there. So we have r over y, r over x, and x over y. And now, since there is a possibility of having a point that might have the coordinates, let's say 0, 3, because 0 is an option when we're talking about an angle of any size. We have to make sure that we put qualifiers on these functions here. So now your r will never be able to be 0, because r is the distance of that, or the length of that radius, and there's no such thing as 0 length or negative length for that matter. So we don't have to worry about r, but with the tangent here, we have to make sure that x is not equal to 0, because if x is equal to 0, we're dividing by 0 there, and that's undefined. Here, y cannot be 0, and then, of course, x cannot be 0, and y cannot be 0 here. All right, so this is a reference page for you. So if you're going through your notes with this video, you'll want to make sure that you've got this page to flip back to as we start working through these 6 trigonometric functions for various angles theta. Okay, so we are given this example here. We say let P be the point 1, -3. So I'm going to go ahead and I'm going to white out x, y there and put in the values 1, -3. Okay, so this point here is 1, -3, which means that this length here, that side length y, is 3 units. Even though it's dropped down, so I'm sorry, actually we do need to say that that is -3 units, because sign does matter with this. I was about to say, since we're talking about a distance, sign doesn't matter, but it does when we're trying to find the value for the trigonometric function. Sign does matter. Okay, and so this x side is of length 1, or of value 1 rather, I should say. All right, so I'm just going to first, before we get going, remind us from the last page of what all these trigonometric functions correspond to. So we have y over r, x over r, y over x, r over y, r over x, and x over y. And notice we don't have a value for r yet. We've got to get that value. That's why we reviewed the formula for distance here, or the length of that line segment. So r is equal to the square root of x. Well, that's y squared, but it doesn't, they're added, so it doesn't matter. -3 squared plus 1 squared. So r is equal to the square root of 9 plus 1, which is the square root of 10. And that does not simplify anymore. So now we have a length, or a value, for each side here. So we've got 1, -3, and the square root of 10. All right, so basically all we need to do is plug in, and if we end up with that square root of 10 in the denominator, we will need to rationalize the denominator, which we're going to with sign. So we have -3 over the square root of 10. We cannot leave the square root of 10 in the denominator, so I'm going to rationalize by multiplying the square root of 10 over the square root of 10. And I end up here with -3 square root 10 over 10. Okay, x over r, well, my x is 1, and my r is square root 10. So once again, I need to rationalize here. Just multiply by square root 10 over square root 10. And I end up with square root of 10 over 10. Y over x. So this is -3 over 1, which is -3. R over y is the square root of 10 over -3. So we just write that negative square root 10 over 3. R over X, square root of 10 over 1 is just the square root of 10. And X over Y, we have 1 over negative 3, which we call negative 1/3. All right, Roy, you cool so far? Very good, thank you. Okay, so this next section, and I forgot to put the little notes on here, so I'll tell you what the blanks say when I read it out to you. But we're going to be looking for the trigonometric functions for quadrantal angles. So we're talking about the angles that are formed by the axes. So we have the 90-degree angle, which is pi over 2. We have the 180-degree angle, or the straight angle, which is equivalent to pi radians. We have the 270-degree angle, which is equivalent to 3 pi over 2. And we have a 360-degree angle, which is the same thing that we're looking at here, which is an angle of 0 degrees. So it's gone all the way around, which is equivalent to 2 pi. So if you're following along with your notes, the process of finding the values of trigonometric functions of a quadrantal angle are to first draw the angle in standard form. So there's your first blank there for number 1. And you can see this is a picture of an angle drawn in standard form. That initial side is along the x-axis. The terminal side of the angle for this particular angle is also on the x-axis, which makes it a little bit interesting to look at. And number 2 says choose a point P on the angle's terminal, there's your blank, terminal side. Well, in this case, the initial side is the terminal side. So we've chosen a point P here. And what I say in your notes is don't forget that trigonometric function values of theta depend only on the size of theta and not the distance of the point P from the origin. We saw that in our last lesson, 4.3, when we looked at the 2 triangles that had the same angle theta, except one was double the size. One triangle was double the size, but that angle was the same measurement. And we saw that we ended up getting the same values for the trigonometric functions no matter what size the triangle was. So when you're working with these angles here, you want to make it easy on yourself and put that point 1 unit away from the origin. It makes things nice and neat when you do so. And then we just apply our definitions for the trigonometric functions, which I'll remind us of again. We have y over r, x over r, y over x, r over y, r over x, and x over y. All right, so we have our point, 1, 0. Notice our hypotenuse, in a sense, you really can't see it, but our hypotenuse is also 1. So we're just going to be plugging in a bunch of 0s and 1s here and see what happens. Well, for y over r, we have 0 over 1. 0 divided by 1 is just 0. For the cosine of theta, we have x over r. Oops, I wrote x, which is 1 over 1. or just plain old 1. Y over x, we have 0 over 1, which is just 0. The cosecant, r over y, is 1 over 0. You cannot divide by 0. This is undefined. So the cosecant of theta for a 0-degree angle is undefined. And r over x is 1 over 1, which is just 1. And x over y is 1 over 0. We've got division by 0 again, so we are undefined. Good so far, Roy? Okay. I swear we spend half the time in these lectures waiting for the slide to actually change. And it cuts my mic off while it's changing, so it just feels like forever with the silence. Okay, I'm going to go ahead and give us our guide here. Y over r, x over r, y over x, r over y, r over x, and x over y. There we go. Okay, so now we're talking about the quadrantal angle 90 degrees, which I'll just remind you is equivalent to pi over 2 radians. And we have x and y here, so we've gone left or right, none, and up 1, so we have 0, 1 as our point P, and our radius still sits at 1 there. Okay, so y over r is 1 over 1, which is 1. X over r is 0 over 1, which is 0. Y over x is, 1 over 0, which is undefined. R over y is 1 over 1, which is 1. R over x is 1 over 0, which is undefined. And x over y is 0 over 1, which is 0. And I'm certain that you're cool with all this, Roy. Thank you for verifying. Okay, moving further around the circle here. So y over r, x over r, y over x, r over y, r over x, and x over y. All right, so just notice we have that 180-degree angle here, where our point P now lands at -1, 0. R is still 1. So this is 0 over 1, or 0, -1 over 1, which is -1, 0 over -1, which is 0, 1 over 0, which is undefined, 1 over -1, which is -1, and -1 over 0, which is undefined. Moving forward. And I promise there's a reason we're doing all these. It's to help us build and understand the chart we're coming up on. So Sorry if it feels like I'm wasting your time going through all these. X over R, Y over X, R over Y, R over X, and X over Y. All right, so we have point P, we have our 270-degree angle, which is equivalent to 3 pi over 2, and all the way around to the negative part of the y-axis. So that is the point 0, -1, and R is 1. So we have -1 over 1, which is -1. 0 over 1, or 0. -1 over 0, which is undefined. 1 over -1, which is -1. 1 over 0, which is undefined. And finally, 0 over -1, which is 0. Okay? And we're not going to do one for 360 because 360, let me get a different color. If I went 360, that would put me back at having the terminal and the initial side on the positive x-axis there, which is equivalent. So a 360-degree angle is equal to a 0-degree angle there. So it's not necessary to do it twice. Okay, so this is why we did all that garbage there. It was to figure out which functions are positive and which ones are negative in each of the following quadrants. So notice all functions are positive in quadrant 1. And in quadrant 2, only sine and its inverse, cosecant, are positive in quadrant 2, which means that cosine, tangent, secant, and cotangent are all negative in quadrant 2. And it would be worth writing this side information of what's negative so you're not having to look and see what's positive and then use process of elimination. You'll just have it written there when you want to refer to it. Okay, so quadrant 3, we have cotangent and tangent as the positive functions, which leaves sine, cosine, cosecant, and secant as the negatives. And quadrant 4, we have cosine and secant as positive. So that means sine, we'll go ahead and do its inverse, cosecant, tangent, and cotangent are all negative in quadrant 4. Now, I have never heard this little mnemonic device that your book gave you, but I figured I'd include it in case somebody finds it helpful. I believe when I was a trig student, I just memorized what was positive. And what I would always do on my test is do what they call a mind dump at the beginning of the test. I'd get my blank test and write down stuff like this chart on the top of my paper so that I didn't have to hold it in my brain while I was trying to take my test. But, you know, you may find this little mnemonic device at the bottom helpful. A smart trig class. So A in quadrant 1, all signs are positive. Quadrant 2, S, sine, and its reciprocal cosecant are positive. T, tangent and cotangent are positive, and C, cosine and secant. I don't know, it may be useful for you. I don't, if I had heard that, I might have used it when I was a student, but I just ended up memorizing stuff. All right. So are you good to go forward, Roy? All right. I figured so. Okay, so we're given this information about these certain functions of theta. We're given that the sine of theta is less than 0. So this means the sine of theta is negative. The cosine of theta is also negative. So with these given conditions, they're wanting us to, okay, name which quadrant this lies in. And this is why I said it might be helpful to go ahead and write down which ones are negative so you're not having to figure it out every time. And we find that when theta lives in quadrant 3, that both the sine and the cosine are negative. So theta lies in quadrant 3. And that's it. Okay, so this next one's a little bit more challenging because you kind of have to break it down and think about it a little bit more. Let's go ahead and do that. So we have the tangent of theta equaling negative 1/3. Let me get my black pen back here. Well, we know that the tangent of theta is equal to y over x. And if that's equal to negative 1/3, before we know which value, x or y, was actually the negative one, we have to do a little bit of thinking. And off to the side here, both tangent and cosine are negative because we're told that the cosine's negative here. Both tangent and cosine are negative when theta, that's a bad theta, lies in quadrant 3. So if we think about quadrant 3, and we've got this angle and that point P, we have the possibility of either having the point from this given information here, it could be 1, -3, or it could be -1, 3. Well, if it's in quadrant 3, since both the tangent and the cosine are negative, then we had to move left some amount of units and down some amount of units. So so we would have to have here that y is equal to 1 because we had to give that negative to the x value to move left here. So my tangent of theta, y over x equaling -1/3, that is actually 1 over -3, based on the fact that tangent and cosine are negative, which bumps it to quadrant 3, and the only way to move left is to move in the negative direction. Okay, so, and we know that they both can't be negative because if they were both negative, it would have been a positive value. All right, so we know, let me just draw our triangle here. We have this triangle. We now know that this value here is 3, well, rather, -3. And this value is 1. So we need to find our R value. So R is equal to the square root of x squared plus y squared. So -3 squared plus 1 squared. We're getting the same square root that we were using earlier, square root 10. So R is equal to the square root of 10. And they're asking us, the actual question is, what are the sine and the cosecant of theta? So the sine of theta is given by y over r. So in this case, we have 1 over the square root of 10. As usual, we can't leave that square root in the denominator, so I'm going to rationalize. I thought tangent was negative in quadrant 2 or quadrant 4. I just saw you type that. Let me go back and look. Tangent is negative in quadrant 2. Yes, you are right. And quadrant 4, yeah, tangent's negative in quadrant 4. Cosine is negative, and tangent is negative actually in quadrant 2. So theta is in quadrant 2. Let me pause our video for a moment. Roy and I are going to have a discussion off camera. All right, I've gotten confirmation from Roy that I think we've made the changes necessary. The only changes we needed to make was that it's in quadrant 2. I should have practiced more what I preached and made sure I verified with my little chart of the signs in the various quadrants before I moved forward. That did not change any of the information through here, because we had already stated that x was -3 and y was -1, and that is correct. However, it did change our picture. It flips our triangle the other way. So if this is the origin here and this is theta, then we moved left 3 and up 1 to get to point P, and that's the point -3, 1. So I believe we are safe to move forward with this. Okay, so I was rationalizing the denominator here, and that leaves me with the sine of theta being square root 10 over 10. And then we are also asked to find the secant of theta. The secant of theta is given by r over x. R is the square root of 10. X is -3. We call that negative square root 10 over 3. Good to move forward, Roy? All right. Okay, so now we're going to shift and talk about reference angles. And then we'll move further into this idea of reference angles and how they can be used to find sine functions for regular angles or angle theta. So we want to, we'll use this first drawing to look at the definition here. We'll use this drawing here. So let theta right there, be a non-acute angle in standard position. Once again, standard position has the initial side along the x-axis and the terminal side somewhere else. So let theta be a non-acute angle in standard position that lies in a quadrant. Its reference angle is the positive acute angle theta prime. So this right here is our reference angle theta prime, and this is a positive angle here. So it's the positive acute angle theta prime formed by the terminal side of theta and the x-axis. So the reason I knew, or how I knew that it was the negative side of the x-axis, is because theta prime has got to be acute. So if I were at the positive side of the x-axis, that's theta. That's an obtuse angle. So that's how I knew that we were talking about the negative side of the x-axis there as its terminal side. Okay, so when we're looking at angle theta and its reference angle theta prime, we have some properties that show up here. So if theta lies between 90 and 180 degrees, so we're talking about lying in quadrant 2 there. So when theta's terminal side lies in quadrant 2, then theta prime is going to be given by subtracting theta from 180. And that shouldn't be a stretch of your imagination to think about. If I have 180 degrees, let me get some colors here. If I have 180 degrees and I subtract out my obtuse angle, the only thing I'm going to be left with is that theta prime angle. Okay, so that's for when theta is between 90 and 180. Okay, so when theta is between 180 and 270, and let me give the corresponding radians here just as a reminder. So 90 is pi over 2. So when theta is between pi over 2 and pi, then theta prime is 180 minus theta. That's the same thing as pi minus theta if you're working in radians. And you may want to note that on your note sheets. All right, so when theta lies between 180 or pi and 270, which is 3 pi over 2, then, okay, so notice theta prime here. It's always the acute angle between the terminal side of theta and the x-axis. So we actually have to go back up to the negative side of the x-axis here for this particular theta prime. So to find that, we subtract 180 degrees from theta. Or if we want it in radians, that's theta minus pi. And so just a quick look at how that works We have theta, this whole bigger than 180 degree pi piece. And I subtract out theta. Okay, so I subtract out 180. That's this here. What I'm left with is theta prime. Okay. Last one here on this slide. Welcome, Ansley. Nice to see you this afternoon. You may be a little bit lost unless you've already looked through 4.4, but hopefully you can pick up on the tail end stuff that we have going on here. Okay, so if 270 degrees is less than theta, is less than 360, so 270 is 3 pi over 2 in radians. So when theta lies in quadrant 4, oh, by the way, for this last one, the terminal side of theta lies in quadrant 3. The terminal side of theta for this last one lies in quadrant 4. Okay, so we have 3 pi over 2 is less than theta is less than 2 pi when we're given in radians. Then to figure out theta prime, we take the entire circle, the entire 360 degrees, and subtract out theta. So let me just point out theta prime to you in this diagram. We have the terminal side of theta. We need the acute angle going back to the x-axis. So in this case, we have the positive side of the x-axis creating that angle theta prime. Okay, so in terms of radians, that would be 2 pi minus theta. All right, we'll move forward here. I think Ansley is actually one of my college algebra students. I think she must have just been testing to make sure that she can get into my virtual office here, probably for her homework help video coming up. So she's probably really freaked out by what she saw on the screen here. All right, so we're going to use all of this knowledge that we just gained with adding and subtracting, all that wonderful stuff, to try to find the reference angles theta prime for each of these given situations here. Okay, so theta equaling 210. Well, we know that that falls past that straight angle of 180 degrees, but it's not quite the 270, taking us back around to the y-axis, or 3/4 of the circle. So we need to follow that theta prime is equal to theta minus 180 degrees. So that's 210 minus 180 lands us with a theta prime angle of 30 degrees. So just a quick reminder of a potential picture for that. 210 degrees, there's 180. So we're talking about the terminal side being here, somewhere in quadrant 3. So theta prime goes back to the negative side of the x-axis. All right, 7 pi over 4. It may be easiest to convert this to a mixed number before we move forward. That's the same thing as 1 3/4 pi. Well, 2 pi is twice around, or I'm sorry, is once around. So we're past the 3/4 mark Let's see if I can draw a small little picture here. The 3/4 mark is 1 1/2 pi, or 3 pi over 4. So this thing has come all the way around and landed in quadrant 4. So our theta prime, or our reference angle, is going to go back to the positive side of the x-axis. Okay, so theta prime, in this case, is going to be gotten by subtracting theta from 2 pi. So that's 2 pi minus 7 pi over 4. That's a 7. That doesn't look like a 7, but it is. There we go. Well, we have to have a common denominator to be able to add or subtract fractions. This is really a 2 pi over 1. So I'm going to multiply by 4 over 4 to get a 4 in the denominator there. And that gives me 8 pi over 4 minus 7 pi over 4, which is just pi over 4. So that reference angle there is pi over 4 radians. All right. So we've got a negative 240 degree angle. And I actually had to draw a picture of this thing before I could even work this problem earlier. So we're going negative. So this angle starts at the x-axis. We've got negative 90 degrees, negative 180 degrees. If I went back up to the positive y-axis, that'd be negative 270. So it's somewhere in here where that terminal side of that angle is. So my theta prime, or my reference angle, is going to drop down towards the negative side of the x-axis. So I'm trying to figure out, okay, what is the measurement of that angle there? Theta prime, in this case, is given by, here's how I looked at it. I said, okay, I have a negative 240 degree angle, and if I add back in 180 degrees, so let me just play with my picture here and show you what my thinking process was. Since it's negative, I wanted to add the 180 degrees. That's going to take all of that straight angle out of there. And I'll be left with theta prime, but it'll be negative. And so since I was dealing with a negative angle, I just took the absolute value of it because I know that my reference angles always have to be positive. So this is positive, the absolute value of negative 60, which is a 60 degree angle. Is that okay for you, Roy? Okay, good. All right, this last one is even trickier to think about. Notice there's no degree symbol given there. So you have to assume that this is given in radians. So we have 3.6 radians. Well, I know that pi is approximately 3.14 radians, and pi is less than 3.6 is less than, okay, so if we're looking at our axes, if I travel in that 180 degrees, I've landed at pi. If I go another 45 degrees, that lands me at 3 pi over 2. So 3 pi over 2 is greater than 3.6. Because if I multiply, let me give you a value for 3 pi over 2. And I'm just going to estimate pi as 3.14. So 3 times 3.14 divided by 2, that's 4.71. So 3 pi over 2, this is 4.71, and this is approximately 3.14. So I know that the terminal side of my angle has to live in quadrant 3. And let me draw that on my little picture down here. So the terminal side goes all the way around and it lives in quadrant 3. So the reference angle theta prime I'm looking for is going to head back up to the y-axis. The negative side of the x-axis. All right, so I have that theta prime is equal to theta minus pi, not equals, theta minus pi. So I'm going to subtract out that pi, or that 180 degrees, from theta to be left with theta prime. And theta is equal to 3.6, and I'm subtracting out pi, approximated at 3.14, and I'm left with 0.46 radians. So the actual math wasn't the hard part with that last one. It was just kind of wrapping your brain around what you were looking at and how to proceed forward with it. You good to move forward, Roy? Great. Okay, so I'm finding reference angles for angles greater than 360 degrees or 2 pi, or less than negative 360 degrees, which is negative 2 pi. So the only difference in those is the way you're traveling around the circle there, or the way you're traveling through the angle. So to do this, and did I miss let me see. Let me fast forward one slide and see if I missed putting some information on a slide. I did. Okay, I'm going to go back and I'll I know you're following along with your notes, so you're seeing the part that I left out, but I definitely want to state it for everybody. Having to play with my buttons over here to go back. Okay. Okay, so we're back on this, and I'll just read to you the little paragraph that I left out, and try to do some explaining while I'm talking about it. The values of the trigonometric functions of a given angle theta are the same values of the trigonometric functions of the reference angle theta prime. So, just as a picture, let's say I have this angle theta, and then I have this other angle theta prime. It's a reference angle. What I'm told here is that the sine of theta is equal to and it doesn't have to be the sine, it's any of the trigonometric functions, is the same thing as the sine of theta prime. And in actuality, that should make sense because they have that same terminal side there. So it shouldn't be a big shocker that they have the same trigonometric function value. So the only difference that you may have with the value of the trigonometric functions is their actual sign. And when I say sign now, I'm talking about positive or negative, just depending on that chart we did a few pages ago where it told us which functions were positive or negative in which quadrant. So that may be the only difference that you encounter there. A function value of an acute reference angle theta prime is always positive. However, the same function value for theta may be positive or negative. So now we're to the part that's on the page here. So to find these, you want to find a positive angle alpha less than 360 degrees or 2 pi that is coterminal with the given angle. Draw alpha in the standard position. Use the drawing to find the reference angle for the given angle. The positive acute angle formed by the terminal side of alpha and the x-axis is the reference angle. So I think it'll be easier once we actually look at these last problems here. All right, so we are finding the reference angle for each of the following angles here. I'm missing the page. There we go. All right, so we have that theta prime is given by, well, let's actually think about what this angle is first. I'm sorry. Let's draw a picture. So we know 1 time around is 360. So 360 plus 90 is 450. 450 plus 90 is 540. 540, I'm doing this all in my head. Let's see, 54 and 9 is 63. So this is 630 right here. So 630 and 35 more degrees. So we're looking at our terminal side landing in quadrant 4, which means our reference angle drops back up to the positive side of the x-axis. So I want to take out as many 360s as I need to. So I have 360 minus, well, I need to take out another circle out of there because I've gone around once the entire way. So that's 665 minus the 360. So that's 360 minus 305. And we end up getting a reference angle there of 55 degrees. So let me stop here and make sure that that made sense to you, Roy. Okay, great. Phew. Okay, so let's start with a picture for this next one of 15 pi over 4. So I know that 2 pi is an entire revolution around. And since this is chopped up into fourths, 2 pi is equal to 8 pi over 4. So this entire circle here going all the way around is 8 pi over 4. And then I have another, let's see, 8, there's 9, 10 pi over 4, 11, 12 pi over 4, 13, 14 pi over 4, 15 pi over 4. So it looks like we're in quadrant 4 again. So our reference angle is going to go back up to the positive side of the x-axis. And once again, we went all the way, we went a complete revolution around. So we're going to have to get that out of there before we can work with the angle. So theta prime is equal to 2 pi, that entire revolution minus, well, we've got to get the extra revolution out of our angle. So we started with 15 pi over 4, and I'm going to subtract that 2 pi, but I already know the 2 pi is 8 pi over 4. So I'm going to subtract out that 8 pi over 4, which was that complete revolution that I had before I actually moved towards my theta angle. And that equals 2 pi minus 7 pi over 4. Well, once again, 2 pi is equal to 8 pi over 4, so this is 8 pi over 4 minus 7 pi over 4, and that leaves me finally at pi over 4 as my reference angle. You ready for the last one? All right, well, the last one on this page at least. All right, so let's draw another picture. We have negative 11 pi over 3, and I kind of thought of this one backwards. I said, well, I know that 3 goes into 11, so I did the division here. That is negative 3 and 2/3 pi. And I knew that 4 pi was 2 full revolutions because 2 pi is 1 revolution. So since it's a negative angle, I needed to add back on 2 full revolutions because it would take me 2 revolutions to go past that negative 3 and 2/3 revolutions. So just a picture here. This is, so we have 1 revolution, and I went in the reverse direction since it's negative. So that was negative 2 pi, and since this is in thirds, 2 pi is equal to 6 pi over 3. So that was negative 6 pi, and then I've got 5 more left to go since I had 11. So that's going to put me in quadrant 1. Because when I break that up into thirds, I got 1, 2, 3, 4, 5, and 5 is in that that first quadrant. So the reference angle we're talking about is this one right here. Okay, now to actually find the reference angle. The wind chime stopped and the dog started up. So I have theta prime is equal to, okay, I have my negative 11 pi over 3, and I'm going to add back on 4 full revolutions, I'm sorry, 2 full revolutions, which is 4 pi, Okay, my 4 pi off to the bottom here, so I don't have to do the math inside the problem here. 4 pi, when I write that in thirds, is equivalent to 12 pi over 3. So I'm going to add back on 12 pi over 3, and that takes me to positive 1 pi over 3. So the reference angle there is pi over 3. And I didn't clear you out from the last check, so give me a check if that was okay. All right. Moving forward. Okay, so the values of the trigonometric functions, this is the paragraph I was looking for earlier. Theta are the same as the values of the trigonometric functions of the reference angle theta prime, except possibly for the sine. A function value of the acute reference angle theta is always positive, however, the same function value for theta may be positive or negative. So we're going to practice using reference angles to find the trigonometric function value of angle theta. So first you want to find the associated reference angle theta prime and the function value for theta prime. You use the quadrant in which theta lies to prefix the appropriate sign on the function value in step 1. So this should make a tad bit more sense once we look at a couple of problems here. And I just did something crazy. There we go. Okay. My screen just went to a new screen there for a moment. Went to my dashboard. Okay, so let's see this in action. So we're given the angle, or well, the sine. We're trying to find the sine of 135 degrees, and they want us to find this using reference angles. So it's not necessary to do this, but this skill will come into play later on. So perfect time to practice it and wrap our brains around it now. So we want to find the reference angle first. So theta prime in this case is equal to 180 minus 135, which is 45 degrees. And now we want to use the quadrant in which theta lies to prefix the appropriate sign to the function value in step 1. Well, we figured out that, well, let me draw this. I believe it was in 4.1, maybe 4.2, that we figured out all of the sine functions for the 45, 45, 90. Maybe it was 4.3. Maybe we just did that. It all seems to run together now. And the 30, 60, 90 triangles. So since this is a 45-degree reference angle that we're using, we can use the knowledge that we've already gained. And we figured out there that the sine of 45 degrees is equal to square root 2 over 2. Sine is opposite over hypotenuse, which is 1 over square root 2, but we rationalize the denominator and end up with square root 2 over 2. So what we're told with that last statement is that the sine of 135 degrees is equal to the sine of 45 degrees. And it's got to be positive because the sine is positive in quadrant 2, which 135 degrees lands in quadrant 2. So positive 45 degrees, so the value of the sine of 135 is also square root 2 over 2. Is that okay, Roy? Okay. You hesitated there for a second. I was holding my breath. And this is our last problem to look at. So we're going to use reference angles to find the exact value of the tangent of 5 pi over 4. And the first thing I did was converted 5 pi over 4 to 1 1/4 pi. So if we want a quick picture of that, here's 1 pi, and then another fourth lands there, so that's going to put us for that original angle theta in quadrant 3. And the tangent is positive in quadrant 3. And I'm going to double check that before I move forward with the blunder that I had with that last one. I'm just looking back in my notes. Yes, the tangent is positive in quadrant 3. Okay, so we first want to find the reference angle. So theta prime is equal to theta minus pi, and that's 5 pi over 4 minus pi, which is the same thing as 4 pi over 4, and that leaves us with pi over 4. All right, so once again, here's our little triangle to look at. Square root of 2, 1, 1. And the tangent is the opposite over the adjacent. Pi over 4 is 45 degrees, by the way, so that's why I use the 1, 1 square root 2. Okay, so opposite over adjacent from either of the 45 degree angles is equal to 1 over 1 there. All right, so the tangent of 5 pi over 4 has to equal the positive, because remember tangent's positive in quadrant 3, positive tangent of pi over 4. The tangent of pi over 4 is 1 over 1, so this value is just 1. And that's all I got for you today, Roy. Do you have any questions about anything? All right. Roy says nope. For those of you watching the video, I know you can't see the chat window, but he says nope. So I'll just say happy studying. I will be putting together your tests this weekend, and so for those of you that are already ready to take it, you don't have any desire to listen to or watch the test review, I'll be doing the test review next Wednesday. I believe the date for your test is not this coming Monday, but the following Monday after that, which I believe is the 23rd, is the due date for your next test. There's some questions from Fort were based on items covered in this section. Oh, good to know. I'll have to go back and look at some of the 4.3 homework questions. Good. I'm glad you're less confused and not more confused now that we've been through the lesson. Roy, if you know some specific questions that use this material in 4.4 that are asked in 4.3, if you don't mind hitting that ask your instructor question key to send them to me so I can take a look at them and be prepared if anybody else sends me questions about them, I would really appreciate it. Very good. So I'll do the test review next week. Test will be due Monday, the 23rd, as well as the homework for this section. But as soon as I post the test, it'll be open for you to go in and take if you don't want to wait on the test review. Other than that, have a wonderful weekend. Thanks again, Roy. You too. Bye-bye.